So I'll be presenting my first place solution to the Monte-Carlo Research Strength Prediction Competition. The agenda, be giving a little background about myself, then I'll be giving a summary of my solution, then I'll be talking about feature selection and feature engineering, then I'll be talking about training methods, important findings, and a simplified solution. So background about myself. I'm a software engineer, mostly do back-end work, which involves a small amount of machine learning, but there's a lot more data wrangling and inference than training. Academic background, I double majored in computer science and math at the University of Maryland. And as a hobby, I've been working on Kaggle competitions intermittently for the past few years. And I've done well in enough competitions that Kaggle gave me the competitions master title quite a while before the start of this competition. Solution summary. So first of all, I take the Ludi game rules, essentially the game code, and I feed them to a Monte-Carlo tree search, which does a brief search on the starting position in order to compute a supplemental game balance feature and additional features describing how quickly the tree search can be run on that particular game. And then I take those supplemental features and all of the ones that most other competitors were using, namely the numerical and categorical game features and the categorical agent features, and I feed them to a stacked ensemble of CatBoost, LightGBM, TabM, and isotonic regression models. The isotonic regression models essentially rescale the raw predictions from the initial models and basically rescale them to a saner range. And then both the raw predictions and the rescaled predictions are fed to weighted averaging, which produces the final predictions. Feature selection and feature engineering. So this plot here shows the feature importances of the top dozen or so features as assessed by my CatBoost models. One detail that's not too visible in the diagram earlier is that each of those model blocks is really 20 models. So there's some error bars here where from the models not all assessing the features as equally important. So most important feature, all the models agreed about this, was the supplemental balance metric, which is computed by the tree searches. And then the next half dozen most important features are essentially the descriptions of the two agents that were playing the games. The next most important feature after that was the player one advantage metric that was provided by the competition organizers, which is computed by essentially playing games between random agents that just make random moves. That's not quite as valuable of a balance metric as the one computed by the tree searches. After that, it's a couple supplemental features describing how fast the searches can be run. Those are semi-redundant with the features provided by the competition organizer describing how quickly random playouts can be executed. After that, it's a few metrics describing the games, like the game tree complexity. And there's a bunch more features like that which didn't make it into this plot of the top features. And then after that, it's the playouts per second, which is provided by the competition organizers. This just shows the CatBoost models, but I'm pretty sure that the LightGBM and TabM models assess the importance similarly. So this is a slightly deeper dive into the most important features. So essentially, the balance feature that was computed by the tree searches was more strongly correlated with the actual mean agent one utility across all agent pairs for each rule set than the advantage P1 that was provided by the competition organizer. And that's illustrated in the scatter plots to the right. Essentially, advantage P1 versus the mean agent one utility is a very noisy correlation, whereas the tree search based metric, it's a less noisy correlation. And as a result, the models found that the tree search based feature was more useful. And their predictions, these partial dependence plots here, they show how the predictions are correlated with the tree search based balance metric. And the models very consistently showed a linear correlation, or a positive correlation, but not linear. And they interpolated slightly differently for the tree searches, or for the decision tree based models versus the neural network TabM. As for how I selected, well, oops, sorry. So there are multiple different tree search variants that could have been used to compute those supplemental features. The way I decided the configuration to use kind of went in multiple stages. So first, I computed those supplemental features with a bunch of different variants and plotted how their predictions are correlated with the actual mean agent one utility across all agent pairs for each rule set. And I checked how that scales for different runtimes with different configurations. And broadly speaking, the configurations were clustered into good configurations and bad configurations, with the good configurations towards the top of the plot. And something that all of the good configurations had in common is that they all use some sort of upper confidence bound-based selection policy and either random or NST playouts. The other settings weren't as important. And then after picking a couple relatively good configs, I then essentially started feeding features that were computed using those configurations to my models and checking how their cross-validation scores. Basically, I checked how well the model scored with features from each different config. Something else that's sort of important to highlight here is that there's a pretty good correlation, even if you only do a search for like 15 or 16 seconds. More specifically, these 16-second searches are roughly as good as 1 hour of actually simulating matches between non-random agents. And that's on the order of like 200 times more efficient. And this is what allowed me to get away with running the tree searches in the submission notebook. If it was taking hours per rule set, that would not be viable. Training methods. So I did 10-fold group k-fold shuffle cross-validation repeated for 3 seeds typically. I was grouping on the rule set names, so no leakage from training versus cross-validation. And the randomization was essentially randomizing how the rule sets are grouped into folds. That's what the random seeds were for. That's something that was not supported by scikit-learn prior to this competition, although I see that they recently added support for it. And in the submission notebook, I used the models from 2 seeds, so 2 times 10 models. The isotonic regression models were trained using out-of-fold predictions as features. I tuned the ensemble weights in order to basically minimize root mean squared error on my cross-validation using Newton-Elder-Mead. Data augmentation. So all of the tree search-based features were computed 10 times. And I would intentionally expose my models to a lot of the random variation in those features. So I'd train them on randomly selected feature values from 9 runs and hold 1 run out for cross-validation. Sometimes the machines that were computing these metrics would run faster or slower in some runs. So I found that it's sort of important to hold out 1 run because none of the training runs would be quite exactly that speed. The random play-based features were more computationally demanding to compute, so I only recomputed the ones that were provided by the competition organizer once, and then I randomly interpolated between the values from the competition organizer versus the values I computed in order to sort of expose the models to the random noise there. And then additionally, I generated and trained my models on some supplemental data. More specifically, I generated an extra 14,000 rows for close to 500 extra unique rule sets. The extra rule sets were generated via 2 different means. One was I implemented my own version of Kaggle, which was not open source at the start of this competition. And then the other was ordinary off-the-shelf instruction-tuned LLMs with few-shot prompting. And I also dropped 43 features, which seemed impacted by Ludi player version discrepancies. So to elaborate on that a bit more, I observed that when recomputing the features provided by the competition organizer on my machines, I got different results consistently for some of the features. And I assume that's probably because of some sort of Ludi player version discrepancy. And I found it beneficial to drop those features. So important and interesting findings. I think the most important thing to highlight is that the search-based game balance feature was extremely useful. That improved my scores on the leaderboard by close to 0.01 or a bit over 0.01. And that's what initially got me to first place on the public leaderboard and is what probably would allow me to hold on to the first place spot. I think that some of the other competitors had better data augmentation strategies than me, but this supplemental feature was beneficial enough to outweigh that. Additionally, those supplemental features are pretty computationally efficient to compute, which is what allows me to get away with generating them. Another thing I'd like to highlight is that the supplemental training data I generated was only marginally useful. There was a slight improvement in the third decimal point on the leaderboard, both cross-validation and leaderboard. And I suspect the reason this wasn't very useful was that it consumed an egregious amount of CPU time in order to annotate these supplemental rows. In order to save CPU time, I tried reducing the number of matches played per agent pair, which caused the labels to be rather dirty. With the benefit of hindsight, I wish I had added half as many rows with double the compute per row, just to make the labels less noisy. Simplified model. So with only my cat boost models and the isotonic post-processing, I can score 0.421 on the private leaderboard, and that's good enough for fourth place. And additionally, roughly half of the 600 or so features are not very important and can be dropped with only a very slight score degradation of 0.001. And this plot here shows it's from a fairly early experiment with light GBM where I was checking how the cross-validation error scales with the number of dropped features. And I found that dropping the unimportant features was not beneficial, but it didn't really cause a huge amount of harm either. I can drop half the features with only a very slight degradation. Okay, Q&A. Do you guys have any questions for me?